Now in this lecture we start a new module on energy band diagrams. This is a very important topic in device modeling, so we will discuss this in detail. At the end of this module you should be able to explain how the wave nature of electrons restricts the allowed energy E of electrons subjected to a periodic potential to certain energy bands. You should be able to outline the features, methods of determination and utilities of EK and EX diagrams of a semiconductor. You should be able to explain the concept of crystal momentum, determine the effective mass, group velocity and crystal momentum of an electron having an energy E from the EK diagram. Sketch and explain the EK diagrams of silicon and gallium arsenide. You should be able to determine and sketch the EX diagram of a uniform semiconductor under the following conditions: equilibrium for any doping and temperature, applied bias, and uniform volume generation. You should be able to determine and sketch the EX diagram of a spatially non-uniform semiconductor under equilibrium, in which the doping and the composition change abruptly at a point as in a heterojunction, and when the doping and composition change gradually. You should be able to explain how the energy band diagram can be used to derive the exponential increase in the diode current with forward bias. Sketch and explain the EX diagram of a P plus N junction under high forward bias. And finally, you should be able to sketch the one dimensional band diagram, that is the EX diagram, and interpret a two dimensional band diagram, that is E as a function of x comma y of any device. So you see, we want to really develop the ability to draw and interpret band diagrams under a variety of conditions. That is the goal of this module. Now let us start with what is an energy band diagram. In the first level course on solid state devices, you have already drawn energy band diagrams for PN junction, bipolar transistor and MOSFET. So what were those like? Here is an example where we show E naught as a line and in parallel with it lines EC and EV. So in this diagram the x represents the distance and the y axis is the energy. Now you know that there can be many other lines in the band diagram, such as Fermi level, donor level and so on. We shall come to those lines in a moment. Here we are only giving an example of an energy band diagram, and we want to appreciate what these lines mean. So like the field lines of force and equipotential lines, energy bands is a powerful concept which expresses physical conditions through a set of lines. So you have already come across lines of force, equipotential lines, right? For example, let us look at a parallel plate condition like this, where you have a small electrode here, say positively charged. So here you have positive charge and you have negative charge on this, and if you were asked to draw the field lines, they would look something like this, right? These are field lines of force. One could also draw the equipotential lines here. They would be perpendicular to the field lines at any point. So I have already come across these lines. For example, this is an equipotential line. Here is another equipotential line, right, and so on. So these lines indicate physical conditions within the device. So for example, if you look at this line, it tells you if I were to place a test positive charge here, which direction would it move? It would move in this direction. On the other hand, if I place a charge here, it would move in this direction, okay, and so on. So like lines are used in this case to represent physical conditions, energy bands also consist of a set of lines which express physical conditions. So for example, here, as you know, EC is the edge of the conduction band. So electrons which are in this band of energies participate in conduction, that is why it is called conduction band. And similarly, EV is the top edge of the valence band. Now I could look at the condition at any x in the device, let us say at this x. Now the slope of this line indicates the electric field conditions within the device. You would recall this from the first level course. You could draw another set of lines giving more information about the behavior of electrons in a crystal. Now this is called an EK diagram. So as against an EX diagram, where you plot allowed energies for electrons as a function of spatial distance, in this diagram at any x such as this x, you are plotting the allowed energies as a function of what is called the momentum of the electron in a crystal. Now this momentum is called the crystal momentum. The crystal momentum is very different from the instantaneous true momentum of an electron, which is the momentum as we understand it, right. So we will discuss this aspect in detail later. Right now we only want to show what are the different types of lines that are indicated that are used in the energy band diagrams. So at any x, E versus K could look something like this. So this represents the energy as a function of crystal momentum. Here the minimum of this EK line corresponds to the conduction band edge, and the maximum of the EK line over here corresponds to the valence band edge. So this is the behavior of electrons in valence band. What is the energy of the electron in valence band as a function of momentum, and this line represents the energy as a function of crystal momentum in conduction band, okay. So the top of this line here corresponds to the top of the conduction band. So we are going to discuss this aspect in more detail. Right now we are presenting the set of lines which are used in an energy band diagram to represent physical conditions. The EK and EX band diagrams complement each other. So you need to understand both these diagrams, the EK and the EX diagram, right, to really derive information about energies and momentum and velocity and so on of electrons in a crystal. Now why energy band diagram? We want to build up a motivation for understanding the energy band diagram, right. So we need to know why, we need to answer the why question. This is what Herbert Kromer, who got Nobel Prize in 2000 for the development of heterostructure for high speed and optoelectronic applications, said about energy band diagram. If in discussing a semiconductor problem you cannot draw an energy band diagram, this shows that you do not know what you are talking about. With the corollary, if you can draw one but do not, then your audience will not know what you are talking about. So the energy band diagram of a semiconductor device is really very important to understand the device operation and also to communicate your understanding of device operation to others. Let us look at Ex and Ek diagrams separately. The Ex diagram, such as the one drawn here, helps us analyze the distributions of electrons, holes, electron current density, hole current density, electric field and psi within a device. You would recall that in earlier modules we have said that we can understand everything about a device if you know n, p, jn, jp, e and psi as a function of space and time within a device. So the energy band diagram really reflects the variations of these quantities. Okay? Now I must mention here that not all lines are indicated here, and therefore just from these three lines you won't be able to figure out all these quantities. Okay? So we will look at this point in more detail later. Now for example, Shockley, who won a Nobel Prize in 1948, used the Ex diagram to derive the exponential increase in the diode current with forward bias. So this is an example to show how an important aspect of diode operation was analyzed and concluded based on energy band diagram. The Ek diagram. Now what does this give you? Now the Ek diagram yields you the group velocity, the crystal momentum and effective mass of a carrier, which can be hole or an electron, for a given energy E. Now the electron velocity in a crystal is a group velocity, the electron momentum of interest in a crystal is a crystal momentum, and the electron mass of interest in a crystal is an effective mass. Okay? And from a knowledge of these quantities, the Ek diagram helps us analyze the interactions of a carrier with the phonons, photons, impurities and other carriers in the crystal. These interactions are governed by the laws of conservation of energy and momentum, namely the crystal momentum. Now, so we have understood what do we mean by energy band diagram, what kind of lines we are talking about, though we did not mention about all the lines that are used in energy band diagram so far. In the first level course you would have come across these lines. However, when we discuss further, we will assume that you are not aware of energy band diagram much, and now we want to develop the concept of energy band diagram from first principles. That is what we are going to do now. Let us start with the qualitative model. We have discussed this point that any model should first be developed qualitatively, okay, and the quantitative model should only follow after qualitative understanding, which involves logical reasoning without the use of any intricate equations. Now we know that an electron subjected to a potential Ux, which varies slowly on the length scale of thermal average wavelength of an electron in a crystal. So here is an example of a slowly varying potential as a function of distance. Let us assume that this length represents the lambda thermal, the thermal average de Broglie wavelength of an electron. The slowly varying potential would mean that over this length scale the variation is small. Now this triangle indicates the amount of variation, the height of the triangle. It indicates the amount of variation over the lambda thermal. Now this is really very small, therefore this is a slowly varying potential as a function of distance. Now if an electron is subjected to such a potential variation, then it can be treated as a particle governed by Newton's second law. Now as against this, an electron subject to a potential Ux which varies rapidly on the length scale of lambda thermal has to be treated as a wave governed by Schrodinger's equation. Now this is an example of a rapidly varying potential over the lambda thermal length scale. So here you cannot treat electron as a particle obeying Newton's laws. For instance, if an electron is coming from this side and hitting this barrier, classical mechanics would say that the electron would just rebound, right? Whereas quantum mechanics would give you a non-zero chance of finding an electron on the other side of the barrier, depending on the width of the barrier and the height of the barrier, right? So this is the important difference between behavior based on wave properties and Schrödinger's equation rather than behavior based on particle nature and Newton's laws. So rapidly varying potentials, you have to use Schrödinger's equation, treat the electron as a wave. Now let us come to a crystal, which is what is of interest to us. So an electron subjected to a crystal potential UCX, which varies periodically on a length scale of A much less than lambda thermal, where A is the interatomic distance. So this is an one-dimensional crystal. In a real crystal, which is three-dimensional, A normally represents the lattice constant. So this A is much less than lambda thermal. Now the way the diagram is drawn here, A appears to be less than lambda thermal, but not necessarily much less than lambda thermal. So the diagram is not to scale. If we really made the A very small, then the diagram would not be clear. Now in this case also, the electron has to be treated as a wave governed by Schrödinger equation. So if you want to understand the behavior of electrons in a crystal, you have to start from Schrödinger's equation and not Newton's laws. Now I would like you to recapitulate from the earlier modules what the crystal potential represents. So you have a regular arrangement of atoms. Each atom has a positively charged core, which gives rise to this kind of a potential variation. So a series of positively charged cores of atoms regularly arranged give rise to this potential, right, periodic potential. However, there are other electrons apart from the electron that you are concentrating on, and the effect of all the other electrons is also absorbed in this periodic potential by making an adjustment in its value, right. So the crystal potential includes the periodic potential due to the positively charged ionic cores of all the atoms adjusted to accommodate the potential of all the electrons other than the electron that you are focusing on, right. So this is an important point one must bear in mind. So in such a case, we need to use Schrödinger's equation to develop the behavior of the electron. Now let us see how do we develop the behavior of electrons in a crystal. One approach is to start from electrons in an isolated atom. So in an isolated atom, your potential variation, electronic potential variation would look something like this. We have discussed this point in sufficient detail in earlier modules. So this is the single atom, okay, location of the single atom, and this is the potential due to the atom. The maximum value of the potential here is referred to as the reference potential, and we call it as E naught, also referred to as vacuum level. And as you move close to the electron, the potential goes to minus infinity, okay. Now the quantum mechanics tells us that an electron in any such potential well will have only discrete energies allowed, right. The electrons can only occupy discrete energies. Now this you already know from the many courses that you have done in physics, chemistry, and maybe even the solid state devices at a fundamental level, that when an electron is in a potential well, only discrete energies are allowed. Let us move on to electrons in a crystal and build up this picture from the picture of an electron in isolated atom. Now the crystal is obtained by bringing in a large number of such atoms close to each other and in a regular arrangement. Now this is what is shown here. So here are a large number of atoms regularly arranged, the interatomic distance being a. So you can regard this isolated atom as a limiting case in which this a has become infinite. Okay? On the other hand, you can build up a crystal by bringing together isolated atoms. So that is what is indicated here. So as you progressively decrease the interatomic distance between various atoms, then you end up with a crystal like this from an isolated atom or a set of isolated atoms. Now how do you build up the picture here from this? Now when you come to electrons in a crystal, each allowed energy level of isolated atom spreads into a band, and the energy levels which correspond to electron away from the atom spread into a wider band than the energy levels which correspond to electrons which are very close to the atom. Okay? The bandwidth is small. Now how do you explain the spreading of a level into a band, which is what is shown here? Well, this can be readily done by applying the Pauli's exclusion principle. Okay? In an earlier module we have explained that all of quantum mechanics related to the behavior of solids can be explained, the quantum mechanical phenomena related to solids can be explained based on just two things, that is Schrodinger's equation and Pauli's exclusion principle. So when you apply Pauli's exclusion principle here to electrons in a crystal, now no two electrons can have the same energy state, and therefore the electrons corresponding to all these atoms, which are very large in number in a practical crystal, should all be different from each other. Therefore a single energy level spreads into a number of levels, right, but which are all closely spaced, and therefore this appears like a band. So the formation of the band from a single level of an isolated atom, the formation of a band of energies, allowed energies in a crystal, from an energy level in an isolated atom can be explained based on Pauli's exclusion principle, which requires that electrons in any system cannot all have the same energy state and therefore same energy. Thus the formation of allowed bands from an isolated atom is what we have discussed just now. Okay? So the approach we have taken develops the allowed bands from energy levels in an isolated atom. In contrast, you can have an alternate approach. You start from free electrons. Now free electrons have a constant potential subjected to them. Okay? While electron in an isolated atom is subjected to a potential well. So these electrons are in a potential well, free electrons are in a region of constant potential. Now we know that for free electrons a continuous band of energies is allowed, in contrast to electrons in a potential well which can only occupy discrete energy levels. Suppose we subject these free electrons to a periodic potential UCX. Now the constant potential can be viewed as a limiting case of UCX becoming 0. So this periodic potential, as its height becomes 0, it becomes the constant potential. Okay? And therefore the movement from free electrons to electrons in a crystal can be seen as a case of increasing the periodic crystal potential from 0 to a finite magnitude. Now that is what is seen here. Now once you have the periodic potential here, then you get what are called forbidden bands. Certain energy levels are not allowed. So while for a free electron all energies are allowed, for electrons in a crystal certain bands of energies are not allowed. Now how do we come to the conclusion that in a crystal certain energy bands will be forbidden for electrons? Now this can be understood from the wave nature of electrons as follows. When an electron is subjected to a periodic potential, the electron wave gets reflected from each of these atomic locations by the periodic potential. Now the incident wave and the reflected wave from each of the atoms summed together can destructively interfere with each other for certain wavelengths. Okay? So it is something like this. So you have these atoms and you have an incident electron wave and you have a reflected wave from each of these like this. Now this reflected wave and the incident wave can destructively interfere with each other and therefore they will cancel each other. In other words, for certain wavelengths no electron wave can exist because of the presence of these multiple atoms and the periodic potential associated with these, which will reflect the electron wave, right, from the location of these atoms. Normally this is referred to as Bragg reflection. Okay? Now when the reflected and incident wave interfere destructively, the wave cannot exist. For all such wavelengths for which the wave cannot exist, okay, the energy associated with the wave is therefore not allowed. So one can find out those wavelengths which will depend on the interatomic distance of the crystal and find out the energies corresponding to those wavelengths, and those energies therefore will not be allowed, as electrons with those energies cannot exist in the crystal. And that is how you get forbidden bands of energies. So this is a simplified diagram representing the formation of allowed bands from allowed energy levels in isolated atom, or formation of forbidden bands from a continuous band of allowed energies of free electrons. Okay? Now these two methods, that is formation of forbidden bands and formation of allowed bands, are referred to as follows. So the formation of forbidden bands from the picture of a free electron, the continuous energy levels of a free electron, is referred to as the Brillouin nearly free electron or single electron approach. On the other hand, the formation of allowed bands from energy levels of an isolated atom is referred to as the Bloch tight bending or LCAO approach, where LCAO stands for linear combination of atomic orbitals. Okay? The wave functions of individual atoms are referred to as atomic orbitals, and linear combination. So you superpose these wave functions to get the picture of a crystal, okay, where you have a number of atoms. So consider the wave functions of every atom associated with every atom, and you superpose them, then you get the picture for a crystal. So this approach is referred to as LCAO approach. So Bloch is the name of a scientist, and so is Brillouin. So the scientist Brillouin proposed the formation of forbidden bands from picture of a free electron, and the scientist Bloch proposed the formation of allowed bands from allowed levels of an isolated atom. So both these approaches can be used, and they have their own advantages. Let us now come to a quantitative model of energy band formation. after a qualitative model we discuss the quantitative model. Now in this we will consider two separate types of band diagrams, namely the allowed energy bands as a function of distance, that is called the Ex diagram when you consider one dimension, right. So E x comma y comma z, so allowed energies as a function of spatial variation of allowed energies, right. This is one type of band diagram. Normally we call it and abbreviate it as just Ex diagram, because most cases we consider the diagram in one dimension, and the other diagram is the Ek diagram. Okay, the allowed energies as a function of the wave vector, the k, the symbol k stands for wave vector, and from the wave vector one can get the momentum of electron in a crystal, the appropriate momentum, that is called the crystal momentum, which we will discuss in detail shortly. Let us start with the Ek diagram. How do you develop the Ek diagram? Consider an electron in a rectangular well. For an example, because we are considering a quantitative model, we have simplified the actual potential picture of electron in an isolated atom. The actual picture is something like this, right. We have drawn U, the potential in electron, electronic potential as a function of distance. It looks like this. Now the mathematics of solving the Schrödinger's equation for this kind of potential is little more complex than that if I approximate this by a rectangular potential well. And so since we want to keep our mathematics simple, we are going to use a rectangular potential well to represent the picture in an isolated atom. Now this well has a height E0, so bottom of the well is potential 0 and the height is E0. We will assume that this height is fairly large, so that you can approximate this well to be an infinite well, and the width of this well is L. Now how will you find the allowed energy levels? You will solve the Schrödinger's equation. So Schrödinger's equation comes out in this form, because the potential energy U is 0. The simple form of the equation is del square psi x plus k square psi x equal to 0, where k square is related to the energy E, potential U is 0, so only the energy E of the electron enters into this picture. So the k is equal to square root of 2 times the electron mass into the energy of the electron divided by the h cross square, where h is the Planck's constant. Also, whenever we are solving an equation, you need to consider the boundary conditions apart from the equation. So the boundary conditions here are that the wave function psi is approximately 0 at both x is equal to 0 and x is equal to L. That is, the wave function goes to 0 at this end as well as this end. Now we are saying approximately 0 because the height of this well is not really infinite, it is large but not infinite. Okay, that is why the approximate sign here. When it is infinite, it will be exactly 0. Okay. So this equation has to be solved subjected to this boundary condition, and this boundary condition is very, very important, because as we will see, it is a boundary condition which says that the wave function should go to 0 at the two ends of the well, which gives rise to quantization of energy and momentum. So the wave function solution for this simple differential equation is psi x is equal to a into e power jkx plus b into e power minus jkx. Okay, the simple second order differential equation. One can easily see by substitution that if you have an exponential with a complex exponent, then when you double differentiate, okay, you will get the form of psi x and the forms of del square psi x to be similar but opposite in sign, so that you will get the sum of these to be 0. The complex exponent can be either positive or negative. Since you have two boundary conditions, you have two coefficients here. Now you can get A and B from the boundary conditions, and the result will be that psi x is given by a constant d into sine of kx, where the kx is coming in the exponent here, okay, and the k is related to the energy of the electron as given in this formula, okay, and this k is coming here in the coefficient of the wave function in this Schrodinger's equation. Now the boundary conditions psi equal to 0 and psi at 0 and psi at L equal to 0 will be satisfied if the k here is integral multiple of pi by L. Now this can be easily understood, right, from all the courses that you have done, so I do not need to spend time in explaining this fact. Now this is where the quantization of energy is coming about. So only certain values of k are allowed. These are integer multiples of pi by L. Note that though the wave function satisfies the boundary conditions with n equal to 0, n equal to 0 is not a solution. This is because for n equal to 0, k is 0 and the energy is also 0, which means that n equal to 0 corresponds to a stationary electron, which is physically not acceptable for our problem. Now this is the quantization aspect coming in as a solution of Schrodinger's equation, okay, and this is what is going to give you the quantization of energy, because the k, the so called wave vector, is related to the energy E by this formula. So if k is quantized, the E also is going to be quantized. So the quantization of k is what is represented here. Let us say this is the k axis, and this represents the 0 value corresponding to n equal to 0. So n can be minus 0, minus 1, minus 2, minus 3 and so on the negative side, and positive side 1, 2, 3, 4 and so on, right. So that is what we mean when you say n is an integer. So that is why we have shown discrete points of k on both positive as well as negative side of k. Now putting this value of k here in this equation, we can get an expression for E as a function of k, and that would be E equal to h cross square pi square by 2 m naught L square into n square, where we have already used the value of k, okay. If you want to write the Ek relation, well, it is just the inverse of this with the square root sign removed. Let me write that on the board. So E is equal to h cross square k square by 2 m naught. That would be the Ek relation, and in this you substitute for k. So this k is equal to n pi by L. So the allowed energies E given by this equation are represented here, okay, for different values of n. Now since E as a function of k is a parabola, that parabola is what is indicated here with a dotted line, and the discrete points of this parabola, which are obtained by intersection of these vertical lines showing the discrete values of k given by this formula, okay, represent the allowed energy states of the electron. These are the allowed energies, the points of intersection. So this formula, when plotted on a graph, would look like this set of points, okay, shown here by red dots. So I have removed the lines to clear the figure to indicate the discrete values of energy and momentum which are allowed for electron in a rectangular potential well. So this is the EK diagram, okay, of electron in a rectangular potential well, where this K represents the wave vector, or it can be used to represent the momentum. So H cross K, quantity H cross K is like the momentum of the electron P, and therefore this can be regarded as energy momentum relationship. Okay, you can easily check that H cross K has the dimensions of momentum. Now if you want to understand this picture physically, what it means is the electron is moving in this well in this one dimension with some velocity, and it is bouncing off the walls, right. So the speed of the electron remains the same as it is oscillating and bouncing off from the walls, right, and the energy and momentum associated with this is what is indicated here. So if the electron has a high energy, it would be moving rather fast and bouncing off more frequently from the walls, right, and for the lower energy this would happen slowly. Now let us look at the picture of free electrons. Now this picture can be regarded as corresponding to the picture of an electron in a potential well of width L going to infinity. Okay, when L tends to infinity, the picture is that of a free electron. Now let us see what happens to these formulae when you put L tending to infinity. So clearly as L becomes larger and larger, your K values which are allowed start coming closer and closer, because pi by L becomes smaller and smaller. Okay. Now this is what is indicated here, that a large number of K values which are allowed will appear on the K line, and the distance between these K values will start coming closer and closer as L becomes large, and in the limit L tend to infinity it will become a continuous line. Okay. Whereas here the K was discrete when L was non-infinite or finite. Now again you put the relation between energy and momentum, the parabolic relation. This is this line, and the points on this line which are intersecting with these vertical lines tell you all the allowed energies, and in the limiting case of L tend to infinity this entire line would be allowed, right, and that is what is shown here. So EK diagram, the EK relation becomes a continuous line for a free electron. As L tends to infinity, this picture can be obtained from this picture of discrete points. These points all start getting very close to each other and they become a continuous line, and therefore allowed energies also start coming very close to each other and become an allowed band. Now this is what is shown here. Now we shall just introduce the picture for electrons in a crystal and stop this lecture, and we will develop the picture in the next class. So let me introduce the picture of electrons in a crystal. So in a crystal you have a periodic potential that is approximated here by this rectangular Ux line. This is called, the symbol for this is UCX, the crystal potential. It is an approximation of the crystal potential. Now here we will assume that the maximum value is U0 and the minimum here is 0. The interatomic distance is A. Now if you solve the Schrodinger's equation for such a periodic potential, then we will find this kind of an interesting EK behavior, where you have forbidden energy bands as shown by these shaded lines, This should not be surprising because you did come across forbidden energy regions here. However, you have allowed energy bands rather than levels. Okay, so this entire band of energies is allowed, and within the band the behavior of energy versus momentum is periodic. Okay, so these are the features of this Ek diagram. So E as a function of k is periodic. Then there are certain bands of energies which are not allowed and certain bands of energies which are allowed. So you have alternately located allowed and forbidden energy bands. And another important thing is, for any given k you have multiple values of energies allowed, whereas if you see here, for example, for any k there is a single value of energy, right. For a given value of energy, of course there are two values of k, one in the positive side, other in the negative side, right. But for any given k there is only one energy. Same is true for the free electron. For any given k there is only one energy, but if you come here, for any given k there are multiple energies allowed. Okay. So periodicity of E versus k, E being a multiple function of k, multi-valued function of k, and existence of alternately located allowed and forbidden energy bands. These are the features of the Ek diagram in a crystal, which we shall develop in the next class. This model is referred to as chronic penny model after the scientists who proposed the above solution for Ek diagram. Okay. And the locations which define the periodicity of Ek are related to the interatomic distance a that is given here. Okay. So we will develop these features in the next class. Now before we close, we just show the allowed and forbidden energy bands existing alternately here, right. So this is an allowed band which is very thin, followed by a forbidden band. Now below this you have a forbidden band. Now this is an allowed band followed by a forbidden band here, then allowed band, and so on. Let us make a summary of the important points of this lecture. So we have pointed out that, like the field lines of force and equipotential lines, energy band diagrams also consists of a few lines which represent very vividly and in the best possible manner the various physical conditions in a device. It is a very important diagram used in the analysis of devices. So the two types of band diagrams are the Ex diagram, where you plot allowed energy levels or energy bands of electrons in a crystal as a function of distance, and the Ek diagram, where you plot at any location in the crystal at any x, for example, the allowed energy as a function of the crystal momentum of the electrons. So normally the crystal momentum is represented in terms of the wave vector k, and therefore this is called the Ek diagram. The Eh diagram helps us to analyze the electron and hole distributions, the electron and hole current density distributions, and electric field and potential distributions in the device as a function of space and time. On the other hand, the Ek diagram helps you to derive the velocity, mass, and momentum of the electron, which are referred to as group velocity, effective mass, and crystal momentum. Now this information is important because the interaction of electrons with other carriers, impurities, phonons, photons, etc. are governed by the laws of conservation of energy and crystal momentum. So one can study the behavior of these interactions based on the Ek diagram. We developed a qualitative model for the energy band formation. Two approaches were discussed. One approach called the Brillouin approach, the nearly free electron approach, or the single electron approach. It consists of developing the allowed band picture of electrons from the picture of a free electron. For a free electron, the entire band of energies varying continuously is allowed. Moment you introduce a periodic potential and subject the electron to this periodic potential, then certain bands of energies become forbidden. So, the formation of forbidden bands is what is the characteristic of the Brillouin single electron or nearly free electron approach. The formation of forbidden bands was explained based on Bragg reflection of the electron wave from the various atomic locations in a crystal and destructive interference of the reflected waves and the incident waves. Okay? So, certain wavelengths are not allowed for electrons, they do not exist in a crystal, and the energies corresponding to these wavelengths also cannot exist, and that is how you talk about formation of forbidden bands. On the other hand, another approach called the Bloch tight binding or linear combination of atomic orbitals approach. Here you develop the picture of electron in a crystal from the picture of electron in an isolated atom. So, in an isolated atom you have discrete allowed energies for electrons. Now, when you bring together a number of atoms to form a crystal, we apply the Pauli's exclusion principle to this system, which says that no two electrons can have the same energy, and therefore the electrons of all the various atoms should have different energies. In this manner, a discrete energy level of electrons in an isolated atom spreads into or splits into a number of levels. For electrons in a crystal consisting of many atoms, and since these levels are all very close to each other because the number of atoms is very large, we refer to this group of closely spaced energy levels as a continuous band of allowed energies. So, formation of allowed bands is the characteristic of this Bloch tight binding or LCAO approach. After developing the allowed or forbidden band picture for electrons in a crystal in a qualitative manner, we then went on to discuss quantitative model for the energy band picture. The quantitative model can be split into two parts, a model for the EK diagram and the model for the EX diagram. Now, we began with the model for the EK diagram, in which we first developed the EK picture for electron in a rectangular potential well based on the Schrodinger's equation, and we showed how application of the boundary condition on the wave function solution results in formation of discrete allowed k vectors for the electrons and therefore discrete allowed energies, and the EK relation is parabolic, but only certain k's are allowed and therefore only certain e's get allowed. So, the EK diagram of an electron in an isolated atom or electron in a rectangular potential well is a set of discrete points all falling on a parabola, which talks about the parabolic relationship between E and K. Next, we showed that a limiting case of this rectangular potential well is the free electron picture, where if you assume the width of the rectangular potential well to go to infinity, you get the picture of a free electron where all the various points on the EK diagram move very close to each other and become a continuous line, and therefore a continuous parabola for E as a function of K is a picture of electrons in a constant potential or free electrons. Then finally we introduced the picture of electron in a periodic potential, and we said that we will develop this picture in detail in the next class, and this picture was that the E versus K relation for electrons in a periodic potential is periodic in K, is multi-valued for a given K. So, you have many energies for the same K and you have an alternate arrangement of forbidden and allowed band of energies. So, we shall continue in the next class from this point onwards.